Welcome to part 2 of our lecture video series for Friday, May 12th, where we are looking at the effect of intermolecular forces as well as molecular shape, size, and mass on physical properties like boiling point, melting point, and vapor pressure. So let's get started by just kind of asking ourselves, if we had to predict a general trend in how boiling point or vapor pressure might change for a substance based only on size, what might we guess? So let's remind ourselves about what is going on with the relationship between boiling point and vapor pressure, because again, they are intrinsically linked. So recall, the boiling point is the temperature at which the vapor pressure of a substance is equal to exactly atmospheric pressure. So vapor pressure happens when you've got a liquid system that is in a closed container, and at some particular temperature, there is a phase equilibrium that is set up between our liquid phase and our gaseous phase, where some of our liquid water molecules occasionally, statistically, make their way to this boundary line between the liquid and gaseous phase, and then they escape up into the vapor phase. They become vapor particles. And the opposite is also true. We have now our gaseous phase water vapor molecules, and one might occasionally encounter that boundary line between liquid and gas and then move back down into the liquid phase. And this happens over and over and over and over again in a constant exchange that we call equilibrium. So the pressure that is exerted by the vapor is called the vapor pressure, as you might predict. So when we are asking ourselves, what trend might we expect on the vapor pressure and then ultimately the boiling point of a substance based on size alone? We need to think about what happens when a molecule maybe goes from being small to large, or compare at least a small molecule against a large molecule, and think about how that will affect the statistical likelihood of a molecule making it to this liquid gas boundary and then escaping up into the vapor phase. So, I don't know, let's consider 3 different molecules. So I'm just going to draw 3 generic molecules. So let's say we have a little linear diatomic. Let's say that we've got a little bent. And then how about we've got something a little more complex, like something you might see in OChem. How about this kind of hexagon arrangement of atoms? Except that's a pentagon. That's fine. Pentagon arrangement. All right, so if I were to rank these molecules from size or mass, this would be the smallest molecule, and this would be the largest molecule. So if I had a collection of each of these molecules in the liquid phase and then put them into a closed container, let's think about how each of these molecules might be affected, or I guess how their vapor pressures might trend just based on their size alone. So in general, what do we know about the relationship or correlation that happens between the size of something or the mass of something and how fast it can move? So typically things that are lighter move faster. So in this first scenario where I've got a bunch of my little diatomics, these dudes are able to swirly twirly move around in that chaotic nature that liquids tend to do a lot faster. So they're really gunning in the liquid phase, at least a lot more than their counterparts will be. Meaning that overall, since we're able to move, since we're nice and light on our feet, so to speak, we are statistically more likely to encounter this liquid gaseous boundary, meaning that it's going to be easier to vaporize or escape into the vapor phase because those molecules were so kind of light and nimble, if you want to think of it that way. So the phase equilibrium here trends towards favoring vaporization. So we can see that the phase equilibrium puts more molecules into the vapor phase. So we would expect that the vapor pressure is higher. Let's compare that to our larger molecules. Let's actually look at the next largest molecule. So let's look at our super chunky pentagon arrangements of molecules. So not only do we have these molecules that are more massive, but they're also kind of like three-dimensionally clunky, meaning they're going to get in the way of one another. And we're going to talk about what that looks like in a moment. But again, things that are larger or more massive tend to move slower. And so compared to this case on the right, where we had a nice, rapid little swirly twirly dance of liquid particles, allowing for more encounters of our liquid with that boundary line, here we've got things that are moving a little more slowly. And that means that statistically, the chance that they have of encountering that boundary line and vaporizing is going to be difficult. So we would expect to see fewer molecules in the vapor phase, just due to the fact that statistically, the slower things are unable to reach that boundary and vaporize as frequently. So we would say that the trend here favors things staying in the liquid phase. So our vapor pressure is going to be lower. We have fewer particles in the vapor phase, so we have fewer collisions, thus our pressure is going to be lower. Which means that this kind of middle guy, which is small, yes, but it is a little bit kind of three-dimensionally clunky. This is going to be somewhere in the middle. So it's small enough that our particles are moving with an okay enough kinetic energy, meaning statistically they are likely to encounter this boundary a decent amount of times, and thus put an okay amount of particles into the vapor phase. Now, I'm not going to say this is maybe perfect. I mean, these are all in equilibrium, right? But in general, this would have kind of a mid-range vapor pressure. So that's vapor pressure. How is that related to the boiling point? So remember, the boiling point is the temperature needed to put every single molecule into the vapor phase. So here, for our smallest molecule, this already favored the vaporization, meaning we've got these molecules in the liquid phase that are moving nice and fast. So if I transfer heat to these molecules, which they can then absorb as increased kinetic energy, they are going to move that much faster, encounter that boundary that much faster, and then vaporize that much faster. So because the vapor pressure is higher, the boiling point is going to be lower. It requires less energy to put these little small nimble molecules up into the vapor phase. So boiling point is lower. This is an example of what we might call a volatile liquid. It's a really high vapor pressure. Okay, compare that to our largest molecule, our heavier molecule. So this is where our vapor pressure is lower. So because we have these super heavy molecules, we are going to need to transfer a lot more thermal energy into this system, or a lot more heat into this system, in order to get these molecules moving with a sufficient kinetic energy such that they can then all reach that liquid gaseous boundary and then all be put into the vapor phase. So because we require more heat energy in order to vaporize everything, our boiling point is going to be higher, meaning that in the middle here, this particular little substance is going to have some boiling point that is in the mid-range compared to the other two. Okay, so there is a correlation that exists between size alone, vapor pressure, and temperature. Now, why is it that I've specified this question as size alone? So this kind of analysis of the relationship between boiling point, vapor pressure, and molecular size is something that we might have done before we understood what was going on with intermolecular forces. So I'm going to split this little conversation up into two videos, because now what I want to do is add on to this question and say, what happens to this trend when you account for the intermolecular forces that are at play between our molecules. So not only do we have this idea of relative molecular size or mass to consider on the effects of vapor pressure and boiling point and things like melting point, but also what now is going on when we include the fact that these molecules are all interacting with one another. So let's talk about that in the next segment of this video.